Today, we're going to take a look at gases. This is chapter 13 in your textbook. And that means when this is for chapter, this is exam 7. So we have 2 more exams after this one, 7, 8, and 9. And just as a reminder, there's no final. The last exam will occur during the finals week on chapter 18. But the next exam will just be on gases, nothing else. All right, so let's find out about gases. Here we go. Those are the topics. Now, I always have the table of contents at the beginning. Just if you want to pause the video there, then you can see the topics that we're going to cover. But I'm going to go straight into it now. Okay, why study gases? There are a number of reasons. This is a good reason. Understanding of real-world phenomenon involves gases to a very greater extent. But historically speaking, gases were the first physical state that modern chemists began to study. After we came out of the Dark Ages in Europe primarily, some of the alchemists morphed into chemists, and some of the chemists they started fresh. But the study of gases was the logical place to begin. For one thing, we've had the equipment, the technology was available to study gases first. Even though alchemists through the Middle Ages were studying all kinds of things, gases, liquid solutions, solids, there was no systematic and what we would consider today a scientific approach. So the technologies that were available to study gases with a quantitative understanding approach were developed first. Studying gases also gives us insight into how science works. Gases, under many circumstances, especially the physics of gases, are such that gases behave the same no matter what the gas is. So oxygen gas, nitrogen gas, helium, water vapor, they all behave the same in many respects. And we're going to cover some of those topics very soon. And because gases all behaved alike, then it didn't matter what gas you studied. You could study a mixture of gases in many cases. The air we breathe was the first candidate for studying gases, even before scientists understood the makeup of the air that we breathe. They could study it from a physical perspective and later on get a better handle on how the chemistry worked. And as a consequence, these early modern scientists were studying gases, and many of the original breakthroughs came through the study of gases, and leading to fundamental properties and concepts involving chemistry. So what is a gas? Well, we know a gas from my youth. I understood from school that a gas needs a container. It needs a container that is complete. It doesn't have any openings in it, because once you put a gas into a container, it will expand to fill that space. Another characteristic of gases is when you mix two gases together or more, they always completely form a uniform mixture we call a solution. So two or more gases mixed together always form a homogeneous mixture, a solution. And that's primarily because there's so much room between the molecules, right? The molecules behave independently to a large extent. So if you want to put another gas in there, there's room for everybody. We know that gases exert pressure on their surroundings. When you work a air pump and fill up a tire, you are taking advantage of this effect. As you put more gas into the tire, you get more pressure. And we're gonna study one of those laws that explains the relationship between pressure and amount of gas. But pressure is exerted on its surroundings and exerted on its container. If you have a gas in a container, it will exert pressure on the walls of the container. We know that to be true because otherwise, if you insert a gauge into an opening in that container, if the pressure were not exerted on the walls of the container, then you would not measure any pressure. The forces would not be delivered to the diaphragm of the gauge and register a pressure. So we know there's pressure exerted by the gas. So if that's the case, we need to define what pressure is. Right? If we're going to be quantitative about this, pressure represented by P is equal to a force per unit area. And because of this factor, because of this ratio, pressure is an intensive property. It's an intensive property because it doesn't matter how much gas you have in that container. Pressure is the same no matter where you measure it, no matter how much gas you have. If you identify a pressure, a value of pressure, then the amount of gas is irrelevant. It's the same no matter where you measure or how much gas you have in the container. Okay? The units of pressure, the SI units of pressure, right? The international system, units of pressure are the Pascal, 1 Pascal. And that Pascal is numerically equal to newtons per square meter. Now that Newton, of course, is named after Isaac Newton. And it represents a unit of force. So force per unit area. But Pascal is a derived unit from Newton per square meter, right? It's not a fundamental unit. This is a fundamental unit, meters. And meter squared, of course, is a derived unit from the fundamental meters. Newton is also a derived unit. And it's based upon Newton's second law of motion. He said that force is equal to mass times its acceleration. Right? So if we know the mass and the fundamental unit is a kilogram, and acceleration is a derived unit, which is meters per second. Okay. Then that means that this is, say, if we have 1 kilogram times meters per second squared, that derivation is equal to 1 Newton. So this is a derived unit And the derived unit is used to derive another unit. The reason that this is the SI fundamental unit is so that you can interchange units, right? We know that this Pascal is a Newton per square meter. But if we enter a Pascal pressure into a calculation, we may have other units in that calculation that need to be canceled or multiplied together. And if it's just a Pascal, then you can't do it at the fundamental level. So you would need Newton per square meter sometimes, or you may even go down all the way to kilogram meters per second squared instead of a Newton. Right? So that would be kilogram meters per meter squared second. This cancels that, that cancels that. So we have kilogram per meter second. Okay, that's a Pascal. Okay, so the point I'm trying to make is that these SI units are adopted in such a way that they are interchangeable. All right, that's enough to talk about that. So this is the fundamental unit. I mean the standard unit of pressure is a Pascal. But historical precedent has given us other units that are more useful for this course. So we just need to know the Pascal and how to convert Pascals from one unit to another. There are other units of measure that will be more useful for us. And that would be the atmosphere. 1 atmosphere. 1 atmosphere is simply the pressure that the air exerts at standard temperature, which would be 0 degrees, and sea level. Right? And that's been standardized. And it's standardized in such a way now that we know that one standard atmosphere is equal to 101,325 pascals. Or we could say kilopascals. So 1 kilopascal is 1,000 pascals. So 101.3 kilopascals is equal to 1 atmosphere. All right. And remember, when we did conversion factors, anytime you have an equivalence, you can make a conversion factor out of it. Put this one on top, this one on the bottom, and multiply it by some value. If you're trying to convert to kilopascals from atmospheres, you would put this one on the bottom. If you were going the other direction, you put that one on the bottom. Right? That's just a reminder of what we've studied in dimensional analysis. Okay. One atmosphere also has other equivalents. So it's also equal to 760 millimeters of mercury. Now, what does that mean? Well, it also equals 760 torr. Right? So 1 torr is 1 millimeter of mercury. Where did that come from? That came from an invention by Evangelista Torricelli in the middle 17th century. And it was a way of measuring air pressure. We now call it the barometer. And any pressure that's given to you by the weatherman or the weather person will be barometric pressure. So we need to know, why do we say millimeters of mercury? It's based upon the construction of the barometer. And that should come in the next slide, I think. We don't need to talk about Blaise Pascal right now. So here's the barometer that Torricelli invented. In Torricelli's day, this was in Italy, and the Renaissance was underway. So this was Italy was the center of scientific investigation, and it was spreading. But two things were necessary to construct this barometer, this measure of air pressure. Besides the theory, we're talking about the mechanics now. You needed a uniform diameter glass tube. And the glass blowers of that day, in Torricelli's day, were masters at producing long tubes of uniform diameter. So that was no problem. He could get all the glass tubes he needed. What he wanted to do was seal one end. All you needed to do is a heat source. You could seal one end, and you can see from right here that all you had to do was just heat it up enough, and it would automatically seal that end. And he left the other end open. Okay. So he took this tube, sealed at one end, and into it he put mercury, liquid mercury. He could have used any liquid, right? It would still work. Why did he choose mercury? Well, mercury was a liquid at room temperature. Mercury was readily available. I mean, it was all over the place. People back then didn't realize just how poisonous mercury could be. So it was used for a lot of things. In fact, it was used in medicine. But what set mercury apart from other liquids was its density. Mercury is very dense. It's about 13.5 grams per cubic centimeter, which is very high, because water, right? The density of water is about 1 gram per cubic centimeter. So if this one's 13.5 times that, what was the advantage to Torricelli? Well, just for comparison, if he had used water in his barometer, his length of tube would have had to been about 35 feet long. But with mercury, with its higher density, he could get by with a tube that was about 800 millimeters long. Okay, so he filled it up with mercury all the way to the top. And then he put his thumb over it and he inverted it and submerged his hand in this vat of mercury. Right, so now we've got this open end on that end, and we got the closed end on this end. Okay, we got our vat of mercury. Okay, so when he released his thumb and pulled his hand out of the mercury dropped, and it dropped to some level. And the distance between here and here at sea level is 760 millimeters. So that's why we say 1 atmosphere is 760 millimeters of mercury. One other thing he noticed was, and he was testing an idea. He believed that the gases, the air that we breathe, has mass, and it bears down on everything on the surface of the earth. So he said, okay, if the atmosphere is applying force to this, then it should be able to lift mercury up that tube if there's no other force up here balancing it. Right? This was, in fact, the first vacuum. Vacuum, by definition, is there's something there, now there's nothing there. There's nothing there now. Used to have mercury, not anymore. Okay, one other thing that he did was he took this barometer and he put it in the back of his ox cart and went up the mountains. And he noticed as he climbed to the top of the mountain, the level of mercury dropped, which indicated that the force on the surface of the exposed mercury was lesser. So as you go up, the column of air above the bowl of mercury is shorter. So there's less mass, less pressure. He did the same thing, went down from his location down to the sea, and he found that the mercury column moved back up. And it settled in the neighborhood of 760 millimeters for sea level. Okay. Once he invented this, and it wasn't just his special invention that he kept to himself, he disseminated his work to other scientists, and they built their own barometers. And some of them just took the barometer and set it on the desk and left it there. And periodically they'd come and check the level. They'd measure the level and they'd make notes as to what were the conditions. And they soon realized that as the weather was starting to get bad, the pressure, the level of the mercury dropped. So low pressure is associated with bad weather. And as the bad weather passed and the sun came out and the weather improved, the level of mercury went up again. So we still use that today. Low pressure means bad weather coming, high pressure means good weather. Okay. There are other uses for this barometer, and I think I have a slide on that. Yeah, I do have a slide. So this device measured air pressure in terms of the height of that column of mercury. That's a good question. How could Torricelli be sure he was measuring pressure and not just total force? What would be a simple experiment that he could conduct to determine whether he was measuring with this height, whether he was measuring total force or measuring actual force per unit area, pressure? Okay, think about it for a second. How would you increase the force on the surface of the mercury? Expand the bowl, make the bowl wider. Now you've got more mercury exposed to air, and if the height of the mercury were proportional to the area, hence the force, then you should see the mercury level go up with more force. So do that, and you find out that no, it doesn't matter how big the bowl is, the level of mercury is still the same. Okay. There are other uses for this device. If you, let me erase some of this. Oops, need to do that. Okay. If you enclose and seal this off, and you take a tube out of here, right? And you have a container here with a gas in it. Okay. The gas is exerting pressure on its surroundings. It's exerting pressure on the surface of the mercury, and you can measure the pressure of the gas inside that device. That's called a manometer. Okay. If this is open to the atmosphere, now what you've got is you've got a pressure in here, right? You've got pressure of the gas in here, and then you've got barometric pressure here. Okay, so the pressure in the gas in the cylinder or the device has to exert pressure on here sufficient to raise the column of mercury and offset the atmospheric pressure. So that's what this picture is showing, that if the atmospheric pressure is higher than the pressure inside the cylinder, then you get the pressure pushing the mercury down here and back up this arm. So that difference is subtracted from the total, and that tells you how much is in here. Or if the pressure inside is greater than atmospheric pressure, then it's sufficient to offset the atmospheric pressure plus support the weight of that column of mercury. Okay, that's a manometer. I will add, for those of you who are in the health sciences and may at some point learn how to take a person's blood pressure. Originally, the Smigmo manometer was a device, just like the ones we use today, has a cuff around it. And it's cinched up snugly to the arm, and it's inflated with air pressure. And the air pressure inside that device bears upon a pool of mercury in a manometer, and you read the pressure off of a device, usually hanging on the doctor's wall. Some doctors don't have them anymore, but some doctors that have been around for years still have a mercury Smigmo manometer on their wall. And you would have to sit close to it, of course, and they'd wrap it on there and pump it up. And what it would do was it would respond, this bladder would respond to the pressure changes in your brachial artery. And when the heart pumped hard, it would press on that gas bag and it would register in the manometer. You see the mercury. And you could tell what the person's blood pressure, the systolic pressure would be the high, the diastolic would be the low. Nowadays, we use a substitute for that so that we don't have to deal with mercury. We use what's called an aneroid device. That is, aneroid means no liquid. So an aneroid Smigmo manometer is the kind that we use now. And some nurses and doctors still wrap that thing around your arm and stick their stethoscope up underneath, and they can listen to the sounds that are coming off of your from your artery as the pressure is decreased from high to low. Those are you'll get these in anatomy and physiology. They're called Korotkov sounds, and there are 5 distinct Korotkov sounds, and you're listening for 2 of them that tell you when to read the high pressure and when to read the low pressure. Okay, enough of that. So this barometer is expanded. It has multiple uses. This is just an illustration that we know that there is air pressure. My dad used to teach earth science in a private school in Atlanta, Georgia. And he loved to do this experiment for his 8th grade class. You put a little water in this empty paint can and heat it up, boil the water, and the water vapor would fill the can and drive out all the air. So nothing inside the can except water vapor. Okay. Then you would turn the flame off and seal the can and just wait. So what happens? As the water vapor condenses back into liquid, what does it leave behind? it leaves behind a vacuum, right? Or very low pressure. And the pressure on the outside of the can is still the same. So if you decrease the pressure inside, pressure outside is now sufficient to crush the can. We know gases exert pressure. This is one example, one demonstration. Okay, so say we need to convert pressure. We need different units of pressure. And with this example, we have the pressure of a gas is measured at 2.5 atmospheres. Okay. And the problem wants us to convert the atmospheres to torr and pascals. So the first one, you need a conversion factor that will cancel atmospheres, right? Numerator, denominator, and leave us with torr. Well, we know how many torr there is in one atmosphere, right? 760. So 760 times 2.5 gives us the value for, let's see. Here we go. Gives us the value for that as 1.9 times 10 to the third. Torr. Now these are the same, they represent the same pressure conditions, right? Like I said before, nature just does what it does and we try to figure it out. And we've given units here, 2.5 atmospheres is equivalent to 1.9 times 10 to the third torr. The gas could care less, right? It just exerts its pressure, and this is the way we try to understand it. Notice also that as the number gets bigger, 2.5 to 1,900, the number gets bigger, that means the unit gets smaller. So the torr is a smaller unit of measure than the atmosphere. Okay. The next one, 2.5. 2.5 atmospheres, and we want to convert this to pascals. So we still need atmospheres on the bottom, but we need pascals on the top. So remember how many pascals are in an atmosphere? 101,000. 325. There we go. So we multiply that one out, cancel our units, and we get 2.5 times 10 to the 5th. Pascals. Okay, so again, the number gets bigger, the unit gets smaller. But we can also compare torr to pascals, right? For the same pressure. You have fewer torr than you do pascals. So the number gets bigger from here to here, the units get smaller. So the pascal unit is smaller than the torr unit. Okay. All righty. We got another one. The vapor pressure over a beaker of hot water is measured at 656 torr. What is this pressure in atmosphere? 656 torr. We want to know what that is in atmospheres. So torr is in the numerator, torr is in the denominator here, and atmospheres, that's the one we want. Right, so what's the relationship? One of those, 760 of these. So 760 divided into 656 is what? It's going to be less than 1. Right? So how much less than 1? 0.863 atmosphere. Here we go. Oh, forgot my units, didn't I? There we go. All right. So, next thing we want to do is introduce the earliest laws concerning gas behavior. Remember from our earlier discussion in the semester, the difference between a law and a theory. Remember, a law just says, this is what happens under these conditions. It's very limited, it's very specific. A theory goes a step beyond that. It says, this is why the law works. This is why it happens. The first one that came available was proposed by Robert Boyle. This is Boyle's law. Okay. And I will add that in order to completely describe the physical behavior of a gas, we need 4 factors. We need to understand volume, temperature, and amount. That little n stands for moles. Moles of gas is amount of gas. So if we know all 4 of those, we can completely describe the physical nature of a gas, as long as it's still a gas. Okay, so what did Boyle work on? Boyle was interested in the relationship of pressure and volume. Okay, how do they vary? When one goes up, what happens to the other one? In order to do that, these other 2 factors have to remain constant. So he had to be sure that this one was constant and this one was constant. And this illustration is how he did it. He used a J tube, right? A long tube of uniform diameter, he just bent it into a J and sealed it at one end. So his J tube was like this, like that, and he just used mercury, right? It worked for Torricelli. Why couldn't it work for Boyle? So he put mercury in here and add a little bit of mercury, it pools up on the bottom, right? Like that. Add a little more, it pools up some more. Add some more, and it touches the inner wall. When it touches the inner wall, this amount of gas in here, the amount of gas, the moles of gas in that section of the tube now is fixed. It will not change because it's sealed off, right? So that fixes this one as constant. The experiment that he's going to conduct takes minutes. Doesn't take very long at all. So the chances that the temperature in the room are going to change is almost nothing. But if you want to be sure that the temperature is constant, just submerge this thing in a bucket of water with ice in it. As long as there's ice and water together, then you know the temperature is constant at 0 degrees Celsius or near that, but it won't change. Anyway, so he kept adding mercury, and he noticed that as he got more mercury over here, the level over here was lower. So what does that tell him? That tells him that this gas in here was exerting pressure. It was exerting enough pressure to push this one up higher, even though he has 1 atmosphere pressure bearing down on this one. So he put more mercury in, right? It only goes up this far. And he put more mercury, and it goes up this far. So what is the actual pressure on the gas in terms of millimeters of mercury? Well, this level here versus this level here. So he had a height of the mercury here. The difference there is the mercury pressure on the gas. But what else is pressured on the gas? Atmospheric pressure. So we had to take H, and this is in millimeters of mercury, and add 1 atmosphere in millimeters of mercury. Now, how did he know this one? Well, he had a separate barometer sitting on the desk, and he could read the air pressure from that barometer and then add it to this value. And that gave him the total pressure. Total pressure on the gas. And he related that to the volume inside here. Right? If he wanted to calculate the volume, easy, right? This uniform diameter cylinder, right, has a diameter, which means we know the area. We know the area inside here times the height equals the volume. So it's easy to calculate the volume. And he just compared as he measured the height, hence the volume, against the height of the mercury plus atmospheric, and he just set up a table. Right? So he had the volume here and he had pressure here. And he noticed that as the pressure goes up, the volume goes down. Okay, they're inversely proportional to one another. Right, so that's what he did right there in black and white. Okay. Right, and there's how you can determine the volume of the gas inside that tube. You just need to know its diameter and plug it in that formula, and you'll get the volume. Okay, so here's a hypothetical situation. And what he noticed was when you multiply this one times that one, and that one times that one, that one times that one, you get the same value. It's constant. So that's Boyle's law. Pressure measured, total pressure times volume equals a constant value. That is Boyle's law. And whenever you see a variable times another variable equal to a constant, it's always inversely proportional, right? If this is constant, doesn't change, then as this one goes up, that one has to go down. Otherwise, that won't be constant. Okay. So when you graph the data, right, he was changing the pressure and measuring the volume, which means the pressure was the independent variable, the variable that he controlled. So it goes on the x-axis. And the response is the dependent variable, the volume. So if you plot them, you get a curve like that. It's a special kind of curve. It's called a hyperbola. Hyperbola has a special characteristic. As you get lower in volume and the pressure goes up, it gets closer and closer and closer to the x-axis, but it never touches the x-axis, ever. Same this direction. As the pressure goes down and the volume increases, it approaches, the curve approaches the y-axis, but never touches it. Okay. That is because of the way this is written. What would happen if this one actually touched the x-axis somewhere out in the distance, way out there? That means that the volume would be 0. And if the volume is 0, K would have to be 0, and K is not 0. It's a non-zero number, right? So it can never touch the x-axis. It can never touch the y-axis. That's a hyperbola. But curves are something that scientists fall back on only when they have to. Scientists prefer straight lines because straight lines are very well behaved. We understand how a straight line works. So, how do we get a straight line out of that? Let's see, there's some more coming up here. Yeah, pressure times volume constant, pressure increases, volume increases, pressure decreases. That's inverse proportional relationship. The line is sloping from upper left to lower right, which is negative. So the slope, the sign on the slope is negative. It's a changing negative slope, right? If we draw a curve here like that, the slope's not the same everywhere, right? The slope here would be like that. The slope here would be like that. So the slope is changing, but it's always negative. Okay. All right, so let's see. P times V is K, that's true, yes. And that's that holds as long as the temperature stays the same. Right? We've trapped the number of moles in that space, so that's not going to change. But the temperature could change. You don't want the temperature to change. Otherwise, the constant will change. All right. Before we get to this, I want to show you how to make a straight line out of that. All right, if we have, need another marker. Pressure times volume equals a constant. Okay, so let's do a little math, a little algebra actually. And let's obey the rules, right? Algebra has rules. So if we divide both sides by volume, right? That's permitted, right? Yeah, algebra permits that. So this volume cancels that volume, and now we have pressure equals K over V. What if we factor this out? And we keep the K, but we factor out the 1 over V, right? That's the same. Notice what we've got here. It looks like Y equals mx plus b. That's the standard form for a straight line. Y equals the slope times x value plus the y-intercept. Right? Well, where's the y? It didn't change. We could say they're atmospheres for argument's sake, atmospheres. But if the volume is in, say, I don't know, cubic centimeters or milliliters, let's do milliliters. So if the volume is in milliliters, what would this value be? Well, remember, whatever you do to the number, you do to the units too. So if we take the inverse of the number, we have to take the inverse of the unit. So the units here would be milliliters to the -1, the inverse of milliliters. Okay. Now when you plot it, you get a straight line. And the slope slope is equal to K. And the y-intercept is equal to 0, 0. Okay, well, that's the origin. That's how you get a straight line out of Boyle's law. Okay. Next, is how do we use Boyle's law? Once the experiment's over, you can't use that K anymore because the conditions may change. You can only use the K for that experiment. Well, let's take that to our advantage. Right? If we measure the pressure times the volume is equal to some constant, and then before the experiment's over, we measure it again. So we measure it this time, the first time, and then the second time, we measure it again, right? During the same experiment. So what are these equal to? Well, this one's equal to K also, isn't it? It's the same experiment. So that means that these two are equal to each other. If A equals B and B equals C, then A equals C. So that's where we get this expression. And this is what I call before after scenario. So if we have a gas that's in a container, we measure the pressure and its volume at the beginning, and then we change the volume. Say we expand it or we compress it. Then we can calculate what the new pressure is. Because if we know this one and that one and that one, we have an equation in one unknown, and we can always solve an equation with only one unknown. Okay, so here's an illustration to say what happens. Okay, if we start off with 1 atmosphere on the left, right, and it has a volume of 1 liter, and the temperature is the same all the way across, then what happens if we increase the pressure to 2 atmospheres? Well, if we double the pressure, then we have to cut the volume in half. So now it's a ½ liter. If we quadruple the pressure, then the volume is 1/4 of what it was to begin with. Right? All right. So here's an example. A sample of helium gas occupies 12.4 liters at 23 degrees C and 0.956 atmospheres. Okay, when you're going to use these formulas and you're working from a word problem, always remember, word problems are designed to confuse. So extract information from the word problem and put it in a format that's more recognizable. The gas occupies 12.4 liters. At what pressure? 0.956 atmospheres. Those are beginning conditions, V1, P1. And the temperature is 23 degrees, which doesn't change. What volume will it occupy at 1.20 atmospheres? So we have a volume and a pressure 2 here. And we're going to change the pressure to 1.20 atmospheres. There's our unknown right there. This way, when you set up the problem, you'll be sure and put the numbers in the correct place. If you put them in the wrong place, you get the wrong answer. All right? So here we go. Solve it for volume, the after volume, before conditions, after conditions, 9.88 liters. So increase the pressure, we have decreased the volume. All right. Okay. So what we're illustrating with this slide is what we will see with gases at different temperatures. Now, gases behave differently. They respond to temperature differently. But if you got a gas, then it will respond uniformly with a change in volume for the temperature. And it is a straight line. This is Charles' law. Okay. Charles' law. Okay. Charles' law is interested in temperature versus volume. So that means pressure has to be constant and number of moles has to be constant. And this is just an illustration of what happens to the volume when you change the temperature. It's a straight line relationship and it's a direct proportion. As the temperature increases, the volume increases for every gas. Okay, so Charles' law is stated as volume divided by temperature equals a constant. And notice when you have variables that are in a quotient relationship, one divided into the other equal to a constant, then if this one goes up, that one has to go up in order for this one to remain constant. That's a direct proportion. And the line will always be a positive slope. So this is nice. We don't have to convert this one to a straight line. It's already a straight line. There's one caveat here. This only works if the value of temperature is always a positive number. Right? If you go down to 0 here, then 0 divided into that is 0. So you've blown your K. And if you go further, now it's negative. So it does not work unless you've got a system of temperature measure where the numbers are always positive. They're never 0. And that system that we use is the Kelvin. Right? So if we have a temperature of, say, 20 degrees Celsius, then to convert to Kelvin, we have to add 273. So that's 293 K. You don't put a degree on Kelvin, you just say 293 K. This is based upon the theoretical 0 point for gases, absolute 0. It was developed by Lord Kelvin, and what he discovered was, for other reasons, if we have Celsius temperature on this scale, and we say the gas behaves like that, but that's as cold as we got it, and it came down here to this volume. Well, Kelvin extended this line down here, and where it intersected here, what he's saying that is if you get the gas cold enough down to absolute 0, then the volume will be 0. Right? We know that's never going to happen because gases have mass and they have volume of their own. But theoretically speaking, this would be minus 273.15 degrees C. We just use 273 because it's good enough for our calculations. So the Kelvin system starts here at 0 and goes up. So the numbers, the values for temperature in the Kelvin system are always positive. And that's a condition that you have to meet when you're doing gas calculations. If you have a temperature, it must be converted to Kelvin. Okay, so 0 would be 273 Kelvin. And that for gases, for our gas law working, standard temperature is 0 degrees Celsius or 273 K. Standard pressure is 1 atmosphere. Okay. That's Charles' law. And directly proportional, yes. That's another way of writing it. If you rearrange this equation, then V equals K times T, right? That works. There's Kelvin. And like I said before, you only have to use 273 added to Celsius to make Kelvin. So what if you have Kelvin and you want to do Celsius? Say you solve your problem for a temperature. And the question asks you, what is that value in Celsius? You just subtract 273 from it. All right. So if we use the same reasoning here for our before and after situation, then we find that V1 over T1 equals V2 over T2, right? Just like before. If that's equal to a constant, that's equal to the same constant, then they're equal to each other. Now, one condition had to be met before Charles could do his work. Notice that Charles was doing his work in the late 18th century, not in the middle 17th century, like Boyle. For Boyle, the technology existed for measuring the pressure of the gas and its volume. That was simple. But before Charles could do his work, someone had to come up with a reliable, reproducible measure of temperature. And that means somebody had to invent a thermometer and the scale to go with it. Okay. So let's see. Oh, I think we talked about that in an earlier chapter. So we had Fahrenheit invented his thermometer, then Celsius invented his thermometer, and then Kelvin came along and modified Celsius to account for absolute zero and temperature in only positive values. But once you've got the reliable thermometer available, you can do temperature experiments now. Okay, so let's suppose a balloon contains 1.3 liters of air at 24.7. That was 1.3 liters of air, and temperature one is 24.7 degrees C. We know we're going to have to add 273 to it. And in fact, the slide may add 273.15. So that's going to be a value. And then we have volume 2 and temperature 2. How do we know to use before and after situation? Well, you're given values for one of the variables. You're given 2 values, before and after. And then the other one you're given maybe before and not after, or after and not before. So in this case, liquid nitrogen, let's see, we put the air and liquid nitrogen at minus 195 degrees C. So that this temperature is 195 degrees C plus 273, will be 195 subtracted from 273 will give us a value. And then we solve for the second volume. Okay. So there's the conversion. There's the conversion for the first temperature. There's the conversion for the second temperature. There's the first volume, and there's the unknown second volume. And it turns out now the volume is only 0.341 liters. So we didn't talk about how to maintain constant pressure and let the volume vary. Well, from an experimental perspective, you can create a cylinder of uniform diameter and put a sliding piston in it. And then you can put a mass on top of it, say, just for argument's sake, 1 kilogram. So the pressure now is constant. And we have the same number of moles in here. So we put it in a bath of some kind and change the temperature, right? So now we can let the volume change with the temperature, and the pressure is constant and the moles are constant. That's how it's done. Oh, and there's a picture example of it. Except now we're on to a different law. Okay, so let's move to the next law. This one is called Avogadro's law. Okay, there were several people doing work, and Avogadro inspired them. So I think the law was developed post Avogadro and credited to him, given his name. What Avogadro said was, if you volume of moles. If you let these two vary, then pressure and temperature must be maintained as constant. So Avogadro wanted to know what would happen to the volume if you change the number of moles, the amount of gas in the container, right? It's a little trickier, right? So it came a little bit later than Boyle's and Charles. And what he found out was, if you double the number of moles in the container, you will double the volume. So we have a direct proportion. As this one goes up, that one goes up, and the quotient equals a constant. All right, that's another way to write it. Just move this one over here. Volume equals constant times moles. And we also can write it this way, just like we did before. Right, that's a before and after situation. Well, that one's inverted, which is fine. It works as long as if we just flip this up to the top, then you get the formula that's there on the screen. This is a direct proportion. Okay, here's an example. If we have 2.45 moles of argon gas occupying a volume of 89 liters, uh, 89.0 liters. So this is initial moles. This is initial volume. So what are we given? What volume will 2.1 mole of argon occupy? 2.1 moles. And notice they tell us it's argon, but it doesn't matter. It doesn't matter what the gas is. It's going to respond the same. under the same conditions of temperature and pressure, the gas will behave exactly the same. So we set it up like that. There's our unknown. Solve for our unknown and find that if you decrease the number of moles, you decrease the volume to 76.3 liters. All right. So before we move to the ideal gas law, there's one other before and after situation. This is called the combined gas law. So it's still before and after, but suppose more than one of these is allowed to vary. As long as you have only one unknown in your final formula, you can solve it. So what's the final formula look like? Well, you notice that pressure 1 times volume 1 equals pressure 2 times volume 2, correct? But what's the relationship between volume and temperature? That. What's the relationship between volume and moles? That. So that's the combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. And all you need is all of these values except for one. If one of them is unknown, you can solve for it. Okay. Now, this also means that these are both equal to the same constant. Okay. What if we don't know before and after? We just know that relationship. What do? Well, we're stuck, right? Unless we know that value. So here's what we're going to do. We're going to say, we're going to fix the units of measure here. Atmospheres here, liters there, right? Moles here, and Kelvin there. So these are our units of measure. That means this constant has to use those units of measure. If we know these values, they're all measured at exactly the same time, then we can calculate that R value. Well, it's called R, the special R, the ideal gas constant. If we calculate these, if we measure these, pressure 1 atmosphere and 1 mole of gas, and 0 degrees in Kelvin terms is 273 K. Then what's the volume? We measure the volume under these conditions, and it's 22.4 liters. Then we calculate that, and it turns out it's 0.08206. Units of measure, liter atmospheres per mole K. Now we have a constant. And as long as we use the right units of measure, this constant will be equal to that relationship. Now it's usually written differently. We rearrange it. So we can write it on one line. Okay. That's the way you'll see it. So if this is constant, and you know any 3 of those other values, it doesn't matter how they got there. You can calculate the unknown. This is known as a state function. We don't know how it got there. We don't care. as long as we use the correct units of measure here and that R value, that constant. So that's what you do if you don't know before and after. If you only know right now, then you go to the ideal gas equation. So here's an example. And let me see. I'm starting to run low on time, so I'm going to see how much more time I've got. We're going to have to move along here. So for this example, it's on the screen, and you set up your P, V, N, and T, and you put in your values, and the one that's unknown, then you know that you've got it in the right place. You extract that information from the problem and then solve for the correct answer. Under these conditions, there you have 3.27 moles in that container. Now, this is extremely valuable in chemistry. When you conduct a reaction in a gaseous state, then you can use this gas law to tell you something about the outcome of the reaction, how many moles of a gas are produced. Okay, here's another one. We're going to use the ideal gas equation, and I'll leave that up there long enough so you can pause it and witness it for yourself. Oh, the difference in this one is we're not given the moles of helium, we're given the kilograms of helium. So what you need to do is you take the kilograms, convert them to grams, and then use the molar mass of helium to tell you how many moles of the gas there are. Then you can use the rest of the equation and solve for the pressure. Okay. So the units that we use here determine the R, because there are several versions of R depending on the units. Okay. But this is the one we're going to be using in this chapter. You got to be sure that your units are correct. If they're not, they have to be converted first before you can plug them into the equation. You can't just throw them in the equation and expect to get the right answer if the units are wrong. There you go. Here's another one. At what temperature does 121 milliliters of CO2 at 27 degrees and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? Okay, the decision here is, what kind of problem is this? Is this before and after, or is this a state function? This is a before and after. Notice you've got a starting milliliters of CO2, and you have an ending milliliters. You have a fixed temperature, but you have atmosphere going from this value to that value. So this problem uses the combined equation. The number of moles is constant, right? So this is deriving the combined equation there. That's the one we're going to use. Since the moles is constant, the moles term drops out. And we only have P1 V1 over T1 equals P2 V2 over T2. And I would set up a table and put in the values for each of those before I tried to stick them in the equation. And then we solve for T2 at 969 K. Now, it wants the temperature in degrees C, right? So we need to subtract 273. Now we know the temperature is 696 degrees Celsius, which is really high. Oh, by the way, we haven't mentioned the ideal gas. So what's an ideal gas? Let me write it on the board since I don't have a slide for it. So what is an ideal gas? As opposed to a real gas. An ideal gas is one that obeys the laws, obeys the gas laws. One, and is a gas at any temperature, even 0 degrees. It never changes from a gas to a liquid or a solid. Right? Now we know that's not a real gas. That's why we call it an ideal gas. Now, under what conditions does a real gas behave like an ideal gas? Well, primarily high temperature and low pressure. If the pressure is relatively low and the temperature is high, then the gas will behave ideally. So what do we mean by high temperature and low pressure? Well, relative to what? Well, low pressure is relative to, say, 100 atmospheres. So 1 atmosphere fits the bill, or in that neighborhood. Right? High temperature is relative to 0 K. So what's high temperature? Well, 273 K would be high. That's 0 degrees Celsius. So under these conditions, 1 atmosphere pressure, room temperature, gases are going to behave ideally. In other words, it doesn't matter the gas, they all behave the same under these conditions. Okay. So we've looked at Boyle's law, Charles' law, Avogadro's law, the combined law, and the ideal gas law. Now we want to look at what do you do if you have a mixture of gases and you want to say something about the mixture. This is important for chemistry because when we conduct reactions in gases, the mixture of gases is going to change very often. You may have a certain number of moles of this gas and a certain number of moles of this gas. They react and they make other gases, the different ratio of gases on the other side. So we want to be able to pull out information about those individual gases. And that's where Dalton comes in. John Dalton, same guy who proposed the atomic theory, was also working in gases. And this Dalton's law of partial pressures states that when you measure the total pressure of a mixture of gases in a container, that value that you measure is actually the summation of the pressure of each one of the individual gases all the way up to however many you have. That's it. Doesn't matter how many gases you have. The total is always the summation of the partial pressures that each individual gas would exert if it were separated from the mixture in its own container. Okay. This pressure is affected by the number of particles. So it's also related to the number of moles of each one. Right? So the total number of moles is equal to the moles of 1 plus the moles of 2 plus on out to the moles of the maximum number. They're related to one another. So if you know the ratio of this gas to the total pressure, you also know the ratio of its number of moles to the total. All right. This just illustrates if you have 1.75 moles of helium in the left-hand one, right here, but if you get a mixture where you have just a little bit of helium and a little bit of neon, a little bit of hydrogen, but the total is 1.75 moles, it's going to be the same pressure as if it were a single gas. Or if you change the mixture, you still got the same pressure as long as the total is 1.75 moles. Okay. All right. The reason it is the volume of each individual gas molecule is insignificant compared to the space between them. They have what we call point volume. And this is the ideal gas again. Point volume. Remember in math class, when you were talking about dimensions, this is a point. It has no dimensions. It has no height, no width, no depth. So when we talk about point volume, we're saying that the gas molecule has no volume. It's there as a point, but it has no volume, right? That's the ideal gas. We know gases have volume, but the distance between them makes the volume of the individual molecules insignificant. All right. Yes, most gas is empty space. That's why you can put 2 or 3 gases together and they always mix, right? Perfect homogeneous mixture every time. The other thing that's required for ideal behavior that I didn't mention earlier is that the forces among the particles must be very insignificant. In other words, when they encounter one another, which they do, they smack into each other. When those molecules approach, and for the time that they're close to each other, there's no interaction at all. There's no repulsion, there's no attraction. They just act like a couple of billiard balls. They bounce off of each other. That contributes to ideal behavior. Okay. So here's an example of a practical use of Dalton's law of partial pressures. If we conduct an experiment and we want to determine how much gas is produced by the reaction, we can collect the gas over water in a jar or a graduated cylinder, whatever the case may be. And notice from this design, we're decomposing potassium chlorate and it produces potassium chloride plus oxygen gas. So the reaction is solid, decomposes into this solid plus that gas. Let's see, I need to balance that, don't I? Let's see, what if I put a 3 here and a 2 here and a 2 here? 2 Ks, 2 chlorines, 6 oxygen, that's balanced. Okay, so we're collecting this gas over water, right? That jar was completely filled with water and inverted, and the gas, as it's being delivered, is displacing the water. What's it also doing? As the gas bubbles through water, what does it do? It picks up water vapor, right? So the gas that's collected over the water is not pure oxygen. It's a mixture. So if you measure the volume, the total volume, you've got a volume of oxygen and you have a volume of water vapor. If you measure the pressure, total pressure, you've got pressure due to oxygen plus a pressure due to water vapor. Okay. So what if we can measure the pressure easily, right? The pressure inside that container is equal to atmospheric pressure because it's pressing against the atmosphere. Now, of course, when the level of the water is up here, then it's also a difference between atmospheric and this height of water. So what you want to do is when you measure the volume, you want to drop this jar down to where the level of the water is equal to the level here. That eliminates atmospheric pressure as a problem. But it does establish the pressure inside now is equal to atmospheric pressure. Right? So the total here would be barometric pressure. Now what we need to know is what's the pressure of water vapor? Well, fortunately, water vapor is very well behaved. So water exerts a vapor pressure of a certain value depending on temperature. And we have charts that tell us what that is. So we look at the temperature and we get the pressure here. And we subtract that from this one and we get the pressure of the oxygen. Okay, there's the reaction I just drew on the board. There it is, balanced. Okay. So there's the chart. If we know the temperature of the water, then we can read it off the chart. Say it's 20 degrees Celsius, room temperature, 25, either one. Then this much torr is exerted, this pressure is exerted by the water vapor. So whatever we get for this one, we can subtract that one, and that's our oxygen pressure. Now, once we have the pressure of oxygen, and we know the temperature of the water, and we know the volume, we've measured the volume, then the moles of the oxygen that we collected are the unknown. Right, we got that one, we got that one, we got that one. So we just need to plug them into this equation. Pressure needs to be in atmospheres, temperature in Kelvin, volume in liters, and we can calculate the moles of oxygen using our gas constant 0.08206 liter atmospheres per mole K. All right, so that's a practical application. Now we got a brain teaser. Suppose we have these two flasks. The one on the left is 2 atmospheres at 9 liters. So we have a volume of 9 liters, right? We have a pressure of 2 atmospheres inside this container. We got a valve. And we got another bulb is only 3 liters and 3 atmospheres pressure. So the volume equals 3 liters and a pressure of 3 atmospheres. So let's say that's 2, and this is 1. All right. And the temperature is 45 degrees, which is constant for the whole experiment. So we don't have to consider temperature. What happens when we open the valve? When we open that valve, what's going to happen? Well, qualitatively speaking, this is the higher pressure. So it's going to move this direction. And the overall pressure then would be decreased. It's less than 3, but over here it would be increased. It would be greater than 2. So the pressure, the final pressure should be between 2 and 3 atmospheres. Okay, how do we determine that? What's the pressure of this helium gas once we open the valve? We have to combine solutions to get the answer. Let's assume that this one is a vacuum first. And what happens when you open the valve and let that go into the vacuum? Well, the initial volume is 9 and the initial pressure is 2. So what, let me give it a different number. Volume and pressure 3. So what's the volume afterwards? Well, it's 9 plus 3 is 12. Right? So what's the pressure of this gas in that space? That's the question. We use Boyle's law. Right? So if we use Boyle's law, let me see if I did that calculation. Yeah. Consider both sides as independent of one another. When you open the valve from the left side, we calculate that the pressure due to the left side gas is 1.5 atmospheres. So this is 1.50 atmospheres. Now let's make this one the vacuum. And let the same thing happen. So the volume is going to be the same. Right? It's expanding into this 9 liters from 3. And then the final pressure can be calculated from that. The final pressure due to that gas is now equal to 0.75 atmosphere. Now we use Dalton's law of partial pressures. The total pressure is going to be due to the gas from this side plus the gas from this side. Right? And that's going to be the summation of 2.25 liters. Atmospheres, excuse me. Atmospheres. Okay. Let's see, 27.4 liters of oxygen gas at 25 degrees C and 1.3 atmospheres, and 8.5 liters of helium gas at 25 C and 2 atmospheres were pumped into a tank with a volume of 5.81 liters at 25 degrees. The temperature has not changed at all, so the temperature is not a problem. We have 27.4 liters of oxygen gas. So what's the question? Calculate the new partial pressure of oxygen. All right, notice that this problem has a lot of information in there that you don't need to solve the problem. That's characteristic of word problems. Like I said, they're designed to confuse. So what's the initial volume of oxygen? 27.4 liters. So the initial volume is 27.4 liters, right, of oxygen, and 1.3 atmospheres. Okay, what's the final volume? 5.81 liters. So what's the final pressure of oxygen? Just solve your Boyle's equation. Right? It also wants to know the partial pressure of helium. Right? You do the same thing with helium. And then calculate the total pressure. Okay, so the first one, we calculate the oxygen with Boyle's law, and we find that it's 6.13 atmospheres. Right? And then we do the same thing with helium. Right? Solve the equation for pressure for helium is 2.93 atmospheres. Add them together, and that's the total pressure, 9.06 atmospheres. We can do that because of Dalton's law of partial pressures. We can treat the gases as independent actors in this experiment. And we only have to add them together once we know the pressure of each one. All right. So let's do a quick review of the scientific method. Right? Reminder, the law is just a generalization of observed behavior. In other words, it just says what happens. It's very limited. If the conditions change significantly outside the parameters of the law, then the law is useless. Right? with a theory, you usually get a model and an idea of what the system looks like. Simplified version, in other words. It's an approximation. And a model is always attached to a theory. It's a way of helping us visualize what's happening at the microscopic level. Okay. Now, that introduction leads us into the kinetic molecular theory of gases. Kinetic molecular theory attempts to explain why all of these laws work. Why do they behave the way they do? Right? And these are conditions, these are postulates. The kinetic molecular theory is based upon these postulates. Gases consist of tiny particles, atoms or molecules, or some of each. Right? Very tiny particles. The particles are so small compared to the distances between them that their sizes don't matter. They can assume, their volume can be assumed to be negligible. These particles are in constant random motion. We have to consider them in random motion because there are billions of them. And we don't have the computing power to track each individual particle on its path and what it's doing when it strikes another molecule or when it hits the walls of the container, right? We just don't have that power. So we have to treat these in a statistical manner. That is, we assume that their motion is random and that they do collide with the walls, and that the collision with the walls is how we measure pressure. That's the pressure exerted on the vessel. Okay. We also have to assume that there are no interactions among the particles, right? They just behave like billiard balls. When they hit each other, they just bounce. The 100% elastic collision, they just hit each other and bounce off. Now, here's a good one too. The temperature of the gas is proportional to the average kinetic energy of all the particles in the container. Temperature is a measure of average kinetic energy. It's not interconvertible, right? In order to calculate the kinetic energy, remember, we need mass and velocity. So you can do it for the individual particle, but doing it for the whole thing is too big a task. We still have to rely on statistical approach in order to estimate this value of kinetic energy. But temperature is a direct measure of the average kinetic energy. All right. So what's the relationship between pressure and temperature? Gas pressure increases as temperature increases because the particles are speeding up. So we can say that much about the particles. If we increase the temperature, we're increasing their kinetic energy. And notice that for the average mass of the particles doesn't change. So what changes? The velocity changes. And when you change the velocity of the particles by increasing their temperature, you increase their kinetic energy. So when they strike something, they deliver more force, and more force is translated into increased pressure. That is part of the theory that explains pressure and temperature relationships. How about volume and temperature? If the pressure is held constant, then this increased kinetic energy is applying more force to that movable piston. And more force means it moves up until the forces are balanced. Now, why does it exert more force at this volume and less force at that volume? Well, if you look at it this way, down here, right, you get impacts that apply a pressure. Right? But if you expand the volume, now the gas has more room, and the frequency of impacts against that piston decrease, because these that were hitting the piston before, now they might go off this direction and hit the wall instead. So if you increase the volume, you decrease the number of impacts and you decrease the force as it increases until the forces balance. That's the kinetic molecular explanation for volume and temperature relationship. Now we could use it for Avogadro's law too. If you stuff more moles of gas in here in that same volume at the same temperature, now you have more molecules at the same temperature impacting that thing, and it dries it up. So adding more moles increases the volume. Okay, so here's a problem that I hope will help us get a handle on what we've studied so far. You're holding two balloons of the same volume, right? So helium and hydrogen both have the same volume. All right, so we've got some questions that we're going to ask about that one, or we're going to complete a sentence. The pressure of the gas in the two balloons are what? They're the same volume, they're in the same atmosphere, they're pushing against the same forces from the outside as inside, so the pressures must be equal. They are the same. They're said to be at equilibrium with atmospheric pressure, right? So pressure volume relationship tells us that if the pressure is the same, the volume has to be the same, and we know the volume is the same. So that justifies our assumption that the pressure inside the balloons are exactly the same. How about this one? The temperatures of the gas in the two balloons are what? They're also the same. They're in equilibrium with the same atmosphere. Plus, they each contain the same volume of gas. So Charles' law says if the temperatures are equal, the volumes have to be equal. And we know the volumes are equal. How about this one? The number of moles of gas in the two balloons. They're also exactly the same, because they're at equilibrium with atmospheric pressure and temperature. Avogadro's law says that if the volumes are the same and the temperature and the pressure hasn't changed, it's the same for both of them, then the number of moles must be the same. Okay. Lastly, the densities of the gas in the two balloons. Remember what density is. Density, mass per unit volume. If the density, helium, hydrogen, the volumes are the same, right? These volumes are exactly the same. Are the masses the same? No. The masses are different. Helium weighs about twice as much as hydrogen. So they will be different. They have the same number of moles of gas, but each molecule has a different molar mass. Right? So the density of helium is going to be higher, is greater than the density of hydrogen, because the mass is greater. Okay? Now this brings us to one of Avogadro's other postulates. He said that if the pressure and the volume and the temperatures are all equal in two containers of gas, then the number of moles must be the same. If the number of moles are equal, then the difference in their mass is due to the difference in the mass of individual atoms or molecules. And that's how we get at molar mass. We start off with gases and we compare equal volumes at same pressure and same temperature and compare their masses for equal moles. Then we can ratio the mass of hydrogen to helium, or helium to nitrogen, or nitrogen to oxygen, and it just cascades. And with that postulate, we were able to establish absolute molar masses for all of our elements. That was in 1865 and afterwards, when Cannizzaro published his paper based upon Avogadro's work. And Cannizzaro said exactly that, only he developed it further. And then Mendeleev in Russia got hold of Cannizzaro's paper, and it helped him with his construction of the periodic table. And then there was one other scientist, Moseley, out of England, in the early 20th century, who established that the periodicity in the table was due to the atomic number. Right, so a lot of people came together to eventually build our periodic table and give us our molar masses and those relationships that are so taken for granted these days. Okay, I got just a few minutes left. Let me see how many slides I've got to go. Yeah, we're getting there. Sketch a graph of pressure versus volume at constant temperature in moles. There it is. That's our hyperbola, Boyle's law. Sketch a graph of volume and temperature. It's a straight line with a positive slope. That's Charles' law. Sketch a graph of volume versus moles at constant temperature and pressure. That's Avogadro's law. It's also a positive slope. So if we have neon in the big balloon and argon in the little balloon, and we know that the volume of neon is twice the volume of argon, that's why I wrote that formula in there. What's the ratio of the masses of the two balloons? All right. Well, what do you think? What's the molar mass of neon? Neon, molar mass is about 20 grams per mole. How about argon? Argon is approximately 40 grams per mole. So if they had exactly the same volume, they'd have exactly the same moles, and the argon balloon would be twice as heavy as the neon balloon. But now you've got a neon balloon that's twice the size of the argon balloon, which means it has twice the moles. So twice the moles means twice the mass, except that argon has twice the mass of the individual particles. So what we've got is two balloons that weigh exactly the same amount. Okay, let's see, we have a sample of nitrogen gas. Sample of nitrogen gas in a container fitted with a piston that maintains a pressure of 6 atmospheres. The gas is at 45 degrees and a volume of 6 liters. You then cool the gas sample. All right, what's going to happen to the gas sample? Final result that occurs once the gas sample is cooled. The pressure of the gas will increase. No. The volume will increase. No. Pressure of the gas decreases. Yes. As you cool it, then the kinetic energy of the molecules decreases and they can exert less force on the piston. So the pressure decreases. How about the volume? Well, if the pressure decreases, then the volume is going to decrease until you get enough impacts from those confined molecules to balance the external pressure. So the volume will also decrease. Oops. Actually, both volume and pressure change until there's a balance. So that slide is inaccurate. The best answer is the volume decreases, but it decreases because the pressure decreases temporarily until it finally balances the external pressure. So I guess with that in mind, D is the best answer. So the gas sample is then cooled to a temperature of 15 degrees. Solve for the new condition. Okay. Oh. If we're looking for temperature, solve for the new condition. What's the new condition? New volume? New volume. So temperature and volume is Charles' law. And if we plug in the values, the actual values, then we find that the volume is 5.43 liters. All right, I gave you the answer to this one earlier when I was showing you the ideal gas equation. Right, you fill in values, 1 atmosphere, 1 liter, 1 atmosphere, 1 mole, 273 K, and 22.4 liters, then you can calculate the R value. If you don't know the R value, or you know the R value, but you don't know the volume, then you just simply calculate it like this. Standard temperature and pressure is 0 degrees and 1 atmosphere. Right, so we convert, we got 1 mole here for N, we got our gas constant there, we got our temperature converted from 0 degrees and 1 atmosphere pressure. Then we can calculate the volume, and the volume should be 22.4 liters. There you go. At standard temperature and pressure for gases. All right, we're a little over, but we're just about finished. So we talked about stoichiometry in the past. When we balance an equation and you're given masses of reactants and you want to find out how much product is produced, that's stoichiometry. Well, we could use stoichiometry with the gases too, because once you have a balanced equation, then all you need to do is convert to moles. Once you have moles, you can go to moles of product. And if the moles of product happens to be a gas, and you know all the other conditions, you can use that to find out the mass of the gas. Or if all you know is the conditions, but you don't know the moles, you can calculate the moles also. Let's look at this example. A sample of oxygen gas has a volume of 2.5 liters at STP, standard temperature and pressure. How many grams of oxygen are present? Well, first thing we need to do is convert. Oh, okay. So we're going to simplify this problem. Instead of using the ideal gas equation as a workaround, we're going to go straight to the molar volume of a gas, 22.4 liters. And convert that to first to moles, and then to grams using molar mass of oxygen. And that tells us that we have 3.57 grams of oxygen. That was the simpler way to do it, yes. This is a second method, ideal gas equation, right? If we plug in the values that we know, right? 1 atmosphere pressure for standard pressure, standard temperature is 0 degrees or 273 K. There's your R value. There's the volume, and we can calculate the moles. And then convert the moles to mass. So either way works fine. Now, for stoichiometry purposes, we have a real world reaction. We have zinc plus hydrochloric acid yields plus hydrogen gas. Right? This is these are aqueous. This is a solid. Okay, so we're going to capture the gas. That's what I'm guessing. 15 grams of zinc and 100 milliliters of 4 molar hydrochloric acid react. What volume of hydrogen gas is produced at 25 degrees in 1 atmosphere? So we have 25 degrees, C, 1 atmosphere. And we want to know, what's the question? Volume. There we go. Okay. So let's see, is the problem, do I need to work the problem out? No, I don't. Go to the next slide. Okay, I've got it animated. Okay. So we need to find out how much hydrogen is produced. So we know that we've got 0.2294 moles of zinc. We converted that using molar mass of zinc, right? So we know how much zinc is produced. How many moles of HCl do we have? 0.2294. Oh, we have to assume that hydrochloric acid is in excess. Let's see if it is. 100 milliliters times 4 is 400 millimoles, right? Or 0.400 moles. And 2 of those, for every one of these, there's 2 of those. This is limiting. Yeah, this is limiting. So that answer is wrong. Only if this is excess. Right? What we were going to say here is how many of these does it take for 0.4 moles? Well, it takes 0.45 moles. It should have taken 0.45 moles. Right? So we're limiting here. So we have to say this is excess. If we say it's excess, then we can proceed. If it's excess, then this is the same number of moles, 1 to 1. Now we can solve using our, oh, maybe I'm not finished. Hold on a second. Oh, okay. I was jumping ahead and thinking that it wasn't going to work. Okay, what we have done now is determined the limiting reagent, and the limiting reagent is this one. So this many moles of HCl will only produce that many moles of hydrogen gas. Oh, no, yes, that many moles of hydrogen gas. Now we convert this to volume using the ideal gas equation. So 4.89 liters of hydrogen will be result from this reaction, and this is limiting. This is excess. There you go. All right. Okay, just a reminder, why is the plot of Boyle's law curve? Because it's an inverse proportion, and plotting it produces a hyperbola. All right, this converts Boyle's law to a straight line that I showed you earlier. That's everything there in black and white, what I put on the board earlier. Okay, that's it for today. We're done with gases. Next time we meet, we'll do a review using the review document that's in Brightspace.